love me now. Because in 2.3, we are done with the limit of the difference quotient. So we have these rules that when we take the derivative of something, so when we take the derivative of a constant, so it's like 5, 6, 0, and such. When we take the derivative of these things, so either d over dx, when we take the derivative of 5, that I just get 0. So when I take the derivative of a constant, so any f of x that equals c, so just some constant, the derivative of that constant will be 0. So the derivative of a constant is 0. So that's the constant rule. And then we have the power rule, which allows us to take an example like this, any polynomial. We can take the exponents, multiply them by the coefficients, and then decrease that exponent by a power of 1. Then I can multiply this exponent times its coefficient and drop that power by 1. And then multiply this exponent by its coefficient and drop that power by 1. So then I don't even have to write x there. And then derivative of a constant is just 0, because this exponent would be 0. 0 times 1 is 0. So then the derivative, using the power rule, is 15 of this red one, of the function, is this. And if you do the difference of the limit of the difference quotient as h goes to 0, it will be this. So that's the power rule. I take any function that has some kind of exponent, like 5, 4, 3, 2, 1, whatever the exponent might be, and you just multiply that, and then you drop that power by 1. So that's its derivative, f prime of x, or you could say y prime. And so that, and that's multiplied. So whatever's out in front, we multiply by the out there. So that is the power rule, which will help save you tons and tons of time. So maybe you'll hate me for making you do the limit of the difference quotient so many times, or maybe you'll love me because now we can use these formulas. And then for these other ones, either radicals or negative exponents, like we can rewrite a radical as a fractional exponent, and then we can take that fraction, and then we can deal with that. We can use the power rule on that. Here, if I have something on bottom and the denominator raised to a power, I can rewrite that as a negative exponent, and then I can go ahead and use the power rule. And then so technically, this can be rewritten as x to the 1/3. This can be rewritten as x to the -4th. And then, so the power rule is only really for one term at a time. And then you'll learn there's other rules that apply, kind of like the limit, how we separate the limit into the sum of the limit, or the limit of a sum is the sum of the limit kind of thing. And so that's how I was able to do that first one. This one, so I can rewrite this 3x to the -2 plus 5 times x to the 1/4, I think that's a 4, plus 2x minus 1, and now I can go ahead and use the power rule on each one of these. So the power rule is really just for one individual thing, but then we have some other rules that allow us to multiply by a constant. Oops, that's a 6. And then this would be to the -3 now, because I got to subtract 1 from that. So this is the constant multiple rule, that I can take -2 and multiply by 3. And then this is the sum rule, because then I just take the power rule of this one and add their two derivatives together. So there's 5/4 x. And then I got to take -1, which is same as 4 over 4. So -3/4. This one's the same, 2, and then this one be 0. So I don't need to write this one. And so that's the derivative of this. So this was the d over dx of this is equal to this. And then you could rewrite this back into your positive exponents. So this would be 3, this would be 5 over 4x, and now x is raised to the 4th root of x cubed, and then plus 2. There's a plus sign in between here. So then you could rewrite as positive exponents and back into the radical. Okay, then so we have some other rules. We have the product rule. So those were sum rules and power rules, constant multiple rule, and sum rule. Now here's a product rule. So when we have things being multiplied. So when I'm multiplying two functions, so f of x times g of x, and I want to take the derivative of that, that's what d over dx means, then I can just take the derivative of the first. I like to put it more probably this way. Take the second, times it by the derivative of the first. I'm running out of room. And then add the first times the derivative of the second. Or you could do it as the derivative of f of x. You could switch those around. I could take derivative of f of x times g of x and plus the derivative of g of x times f of x, right? It's multiplication. We can rework those. So you could also rewrite it like, so that's one notation. You could also rewrite it like this, where it's, so if we have f times g of x, then the derivative of that, would be f times g prime of x would be, and these can switch around. I'm putting g first, plus f times g prime. So that's taking g and times it by the derivative of f plus f times the derivative of g. This just means f times g, right? Or f of x times g of x. All right, so you could write it like that, or you could do it like this. Right, these two mean the same exact thing. Okay, quotient rule, that's the one's a little more difficult. You won't like this one. So if I'm taking the derivative of a division or quotient, then I have to take the derivative of the top. So I'll do it in this form first. Times g of x minus the derivative of the bottom times the top, all over the bottom squared. Okay, so it's the derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. Or you can write it as the little dash there. So we got f prime. So f prime times g prime, or g, minus g prime times f, all over g squared. So you can rewrite it like that. There's the apostrophe in there, the prime. That apostrophe just means prime. So if you have these two functions, you have f of x and g of x, and we want to, say, multiply them. So f times g of x. I usually like to do this one. So when I'm multiplying these two, so to take the derivative of this multiplication, I take the derivative of the first, or take the second, and then take the derivative of the first. So you're going to multiply it by the derivative of the first, which is 2x plus 1, and then you're going to add the derivative of the, or just take the first, not 2x, x minus 2, and then times by the derivative of the second, which is just 3x squared. So that's multiplication. So division, f divided by g prime of x, would be taking the derivative of the top or the second. You can mix the two. So this one matters what you do first. So this one will be taking the derivative of the top, which sometimes I like to put second in this multiplication here. minus the top times the derivative of the second, or the bottom, sorry, all over the bottom squared. So it's the derivative of the top times the bottom, or the bottom times the derivative of the top. You can switch those around. And then minus the top times the derivative of the bottom, or you could switch those around, the derivative of the bottom times the top. But this one, the top has to come first here, and then minus the derivative of the bottom. So it's the derivative of the top comes first, and then minus the derivative of the bottom, and then all over the bottom squared.